Okay, good morning to all of you. In the last class, we learned a little bit about the basic about an CMOS operation as a switch, both nMOS and PMOS. Today we will use that basic knowledge to understand how an CMOS inverter static characteristics. Okay, we are not going to learn about the transient switching, that we'll do it in the next class. Today we will just focus on the DC characterization. Static doesn't mean only zeros and ones. The DC characterization, basically, that would have been a more appropriate term. Okay, because we are going to focus nicely on inverter characteristics, because once you are very clear in these fundamentals, then the complex circuits become very easy. That is why one whole lecture is dedicated towards static characterization, and one more additional lecture is totally dedicated towards transient characteristics. Okay. If you see here, let's again revisit this particular terminology which we are going to use today, and we are going to derive today for certain circuits. Noise margin. Okay. Earlier we said that before the invention of CMOS, we had BJT based logic families. Okay, there the definition of noise margin was slightly different. Okay, now if you see here, for a TTL, this is the data for a TTL circuit where the supply voltage was 5 volt. There the output was defined as VOH, which could be anything between 2.4 to 5 volt. Okay, there we knew that as you keep increasing the fan out, the output would fall a little bit because of the base current which is flowing into the next stage, the output voltage, which we discussed in the very first class. So it was not VOH was not a single voltage, but it was a band of voltage starting from VOH min to output, and then similarly VOL, that means, and the logic level 0 was corresponding to anything between 0 to 0.5 volt, and in between it was forbidden. Okay, so this was in the output stage. Okay, like for the TTL gate specified that for a logic 1, the IC could give any voltage between 2.4 to 5 volt, and logic 0 would mean 0 to 0.4 volt. Okay, so this was the band which was specified as output. Whereas the input, if you consider a gate, anything between 0 to 0.8, the TTL gate considered it as input, and it would work perfectly. Even if you get 0.8 volt, the TTL gate would take it as logic 0. There was no problem with that. Similarly, for the logic level high, any voltage above 2 volt, the TTL gate would take it as logic 1. So if you see here, this is the maximum output which would available 0.4 volt here, but it could take 0.8 volt in the next stage as an input. So 0.8 minus 0.4, which was 0.4, this was known as the noise margin. That means this was the maximum noise the circuit could resist to. Okay, it would be immune to noise as long as the noise was within 0.4 volt. Okay, so that was the definition of noise margin here, for noise margin low. Similarly, like the output minimum output voltage which would be available from any stage of a TTL gate would be 2.4 volt. Whereas the minimum voltage which the next stage would take it as 1 is 2 volt. So even if some noise comes and pulls this 2.4 volt to 2 volt, still it was acceptable, because maximum of around 0.4 volt noise margin was available here. So this was the original concept of noise margin. Okay, so we have a question: in case of CMOS, there is no current. So in the CMOS technology, as rightly brought out, they would be rightly brought out by Rutuja, I guess. So there won't be any band here. So this is how. Then there was another definition which was floated for CMOS topology, in which this was the Yeah, yeah. Can you wrong NMH wrongly, but what is it? Can you just switch on your mic? Here noise margin high, right? Noise margin high is this voltage OH minimum minus okay. This should be an OL. Yeah, correct. So now this was the kind of slopes we started getting it for the CMOS technology, right? So here, if you see here, there was no band of VOH and now no band of VOL. Okay, so let's just first define noise margins here. Here we are assuming VOH is equal to VDD. Again, we'll see this. This is also not necessary condition. They could be VOH could be as less than VDD, or VOH could be less than ground or more than ground also. That is also possible, certain configurations. Okay, so here this was the kind of VTC curve which we got. So we had to define noise margins to understand how to define a figure of merit which represents the immunity to noise. So here what we did was we defined a point VIL, which was the when this slope, when this curve starts falling down with increase in, this is the output on the y axis and input in the x axis. When the output starts falling down, we take a point where the slope is -1. So you drop a vertical line and we defined it as VIL. That means any voltage between 0 to VIL, we assume the output to be high voltage. Okay, so although there will be a small drop here, corresponding to this VIL, but then that was corresponding to the slope -1, but we defined it roughly. This would be the noise margin VIL. Okay, similarly for VOL, we took a point out here where the slope is -1 and any voltage from VDD to VIH. Okay, that was the band of input voltage for which the output would be 0 here. So that will be considered as logic 1 at the input side. Okay, so basically VIL -0 or VIL is the noise margin low, and VDD minus VIH will be the noise margin high. Okay, so these were the two new definitions which came in with the invent of CMOS technology. Okay, so in the very first class, when we learnt about the history of CMOS, we told after BJT came in the CMOS technology. Okay, but what we missed out then was the CMOS technology. When it came in, initially only nMOS was made. So there were a few logic families which were purely based only on nMOS, and subsequently the PMOS also was fabricated and tested, and then the actual CMOS started. So in between BJT families and the CMOS, the current CMOS kind of topology, we had 2 or 3 classes of logic gates which were based only on nMOS, no PMOS. Okay, so among them, the first one was the resistive load inverter, in which we had an nMOS out here and we connected a pure resistor out here. So the basic functioning was like if you give an V in is equal to 0, this would be switched off, and and then you have the VDD out here, and when you give 1 volt here or the VDD here, this will be switched on and VDD will be dropped. There will be current flowing here and VDD will be dropped across this RL. Okay, why slope is used for a noise margin? Okay, here. Okay, so that is just an rough indication that this is going to start, and we have to somewhere mark VIL, right? So slope is equal to -1. It was just taken at a place where this is exactly 45 degrees, this angle out here. So assuming the voltage has started falling down here, right? So that is the reason. There is no, there's just an figure of merit which was defined like that. Okay, so a standard datum was set like that. Okay, there is no specific reason for that. Okay, so obviously when you are giving VIL, the V out won't be VDD. There will be a small drop, but still we assume that. But even that little bit of drop won't affect the next stage. It will still be considered as an 1, which because it is way beyond the threshold voltage of the inverter itself. So that is the reason that voltage was fixed like that. Okay. Okay. Now. So I have a tendency to go fast. So if you keep posting your doubts out here, so that will normalize my speed. Okay. So this is a resistive load inverter. So if you see here, we said if Vin is equal to 0, this will be switched on, and Vin is equal to 1, this will be switched on, and a current will flow that will bring down the voltage VDD. Okay. Now you will in one go you will assume everything is fine with this if you see this topology, but there are small issues. Okay. Now that can be understood from this plot out here. Now I am plotting V0 out here on the x-axis and the current flowing in through the VDD on the y-axis. Okay. Now I have two elements out here. One is a transistor and one is a resistor. So let me plot the both the characteristics out here, and those points which are intersecting, obviously that will be the actual operating points, right? So now if you see here, now for this nMOS out here, okay, V0 is nothing but VDS and Vin is nothing but VGS. So I plot those curves, right? So the characteristics would be the nMOS transfer characteristics. This is known as nMOS output characteristics. Okay, nMOS output characteristics, VDS versus ID characteristics, like for various VGS. So these lines which are going like this is only the nMOS characteristics. Now I need to plot the characteristics of the load resistance also. Now if you see here, when V0 is 0 out here, right, so the current which would flow in this resistance will be VDD minus 0 or VDD by RL. So I take this point here, VDD divided by RL, and similarly when V0 becomes VDD, then there is no current which can flow through RL. So I take this point as VDD, and I join these 2 points because this relation is given by V is equal to IR, right? It is a linear element. Excuse me. So I have put a straight line because it's a linear element. Now if you see, this is one line. Now if you try to analyze this, when Vin is equal to 0, okay, so what is the corresponding point of load line of the resistance? It will be here, and the intersecting point for the Vin is equal to 0 means VGS is equal to 0. So that will come here exactly on the x-axis. So you get a point VDD. So when Vin is equal to 0, you will get an VDD. But if I consider a case where Vin is equal to VDD, okay, logic 1, this is logic 1, right? So VGS is equal to 1. So this is the voltage out here. Okay, this is the max voltage here. Okay, I should have written VDD here. I have worked a lot on 45 nanometer technology, so generally I get fixed to this 0 and 1 volt here. Okay, so this is the intersecting point out here, right? So you will find that this is not an V0L is not 0 volt here. Okay, it is not 0 volt here, but it is more than 0 volt out. So if you see, this curve is not touching the x-axis. Okay, that if I have to explain it here, see, ID is restricted here by the size of this transistor, right? So so unless ID is equal to VDD divided by RL, you can't reach this point out here, right? So that is the reason, okay, you will have this intersection point here. Basically ID is not reaching the required levels out here, so that is why this doesn't reach here. Now there are two ways to make it as close to 0 here. One is increase the value of RL, right. If you increase RL, then this IDRL will be greater, and this will come close to V0. Okay. Now there is a drawback in doing that. If you increase RL, so that much more time it would take whenever I have to switch from 0 to 1. So it will be slow. A big RL will see to that it is going and slowly it is going high, right, this output. So you will have higher propagation delay. The next method of bringing this V0 this V0 H to as close to 0 is by increasing the size of this transistor. So that is basically increasing ID. So if you do that, when the input is 1, a constant current is flowing in the circuit, right, unless the CMOS circuit. So the static power dissipation goes high. So you see here, so there is a compromise has to be done somewhere. So there is some design trade-offs between propagation delay, static delay, and VOH. Okay. Another thing, important thing which we need to remember out here is these kind of circuits are known as ratioed logic. Okay. What does a ratioed logic means is the size of the transistor, okay, and the values of these components which is there in the circuit, they have an effect on VOH and VOL. Okay, so that is the reason we say it is ratioed. That means the ratio of these transistors, the size will finally decide the value of VOH or VOL, VOH and VOL, right. So that is why it is known as ratioed logic. Okay. So that is not the case with an CMOS, it is non-ratioed. We will see that irrespective of the size, you will get the full VDD in that case. Okay. So this is known as a ratioed logic out here. Now, so before further analyzing that circuit, let's just recall the MOSFET current equations. So we know ID when the VDS is very small is given by Kn dash W by L VOV. VOV is nothing but VGS minus VT into VDS. Okay, so here just above 0 here it is like a straight line out here, and then after that it comes into a linear region. So you could call this as subthreshold. No, subthreshold is not the exact value. Let's leave it like this, small VDS. Then we have an VDS slightly more than the small value. It comes into a linear region where ID will be Kn dash, yeah, deep triode. Yeah, that could be an ideal nomenclature. Thank you. So Kn dash W VOV minus VDS by 2 into VDS. So here you will see one VDS is there, one VDS is here. So it is a quadratic form, that it is not linear, it is slightly bending like this, and finally it reaches a saturation region where it is no more dependent on VDS. Okay, so we are not taking into consideration channel length modulation as of now. So it is more or less saturated. So this is the equation, and then everywhere instead of writing W by L Kn dash, and we also use this Kn is equal to Kn dash W by L. Okay, so it simplifies the equation like this. Okay. So if you have to, now if you see here in this particular topology, to calculation of VOH. So for VOH, Vin is equal to 0, and we are assuming that there is no current which will flow here. So VOH is equal to VDD here, right. So there is no issue with this. Now to compute VOL, now there is an resistor out here. So the current in the resistor will be yeah, leakage current, and we are because this is all this family was prior to CMOS. So 230 so the power supply voltages, if you see here, was 5 volt which was used out here. So that a small leakage, this was long channel devices. So the leakage current and all was negligible in those days. Okay. So this came much before PMOS, right? So this logic family. So you find 5 volt and probably 360 nanometer or more. These families were. So that is why the leakage current is an issue for the current class of latest devices, right? So that is why leakage current was neglected out here. Okay, and now trying to compute an VOL. Here, so we have 2 elements. So the current in the resistance will be VDD minus V out by RL, right? And then the current here now towards this region, if you see VDS is small, right? It is close to 0, and hence we have to apply the linear region equation. So Kn by 2 into 2 VDD minus VTO into VOL minus. So this VDS which we said, okay, in this equation, if I go back, this VDS, okay, is now here. We are talking about the VOL out here. So that becomes an VOL here, right? So VOL square. So the VDS becomes VOL, right? So V on should be less than VDD because of a drop in V on should be less than VDD because of the drop in IR. Okay, VOH we are assuming it will be full because we are neglecting the leakage current here. So we are assuming it will be VDD available here. Okay, is it okay? Yeah, yeah, man. So here VDD minus. So we substitute and we equate these two currents out here. Then we get a value of VOL as given here. Okay. So what is important here again to note is, again VOL is an inverse thing, inversely proportional to Kn and RL. That is, if you use a large RL, you will get an VL as low as it will become lower, and similarly if you use a large Kn, that means the size is increasing, still VOL will be low. So this proportionality should be clear to us. Okay. So this is how we calculate the value of VOL is calculated. VOH is going to be VDD, VOL is going to be defined by this equation. Okay. Again it is ratioed. This is what we need to remember out here. So why don't we use a small VDS equation here? We are not assuming it to be too small out here, right? So it is in a linear region. So the small VDS is generally used for very deep, like we said, for deep triode. We are assuming it to be an triode region there. Okay. What is also initial short circuit current is less when the gate voltage is rising. We are not discussing anything about the transient as of now. Okay, we are only talking about the how VOH is equal to VDD. Okay, VH is equal to VDD because we are assuming this is totally switched off. So this total VOH will be available, and since this is going to drive another CMOS gate, so there will be no gate current there. So it will always be VOH. Right. So this is we are not this is not going to drive any other it is going to drive another CMOS gate. So there is no current which is going to be flowing here. So it will be okay. So okay. So now I think okay, now we are trying to calculate VIL. Okay. So now in VIL we are again trying to compute equate the currents. Okay, one is flowing through the resistance, which is VDD minus V out by RL, and here at this point the nMOS has just started conducting. So we are assuming it will be in saturation region. So it will be given by Kn by 2 V in minus VTO the whole square, right? So now here if you differentiate both this left hand side and right hand side with respect to V in, I get 1 by RL dV out by dV in, and this is V in minus VTO. So if you differentiate these things, this 2 gets cancelled, right, after differentiating, and this power goes. And then if you substitute dV0 divided by dV0 by dV, Vi as -1 and also substitute V in to be VIL. So I get the value of VIL as VTO plus 1 by Kn RL. Okay. So this is how.
Sir, one question.
Yeah, tell me.
Sir, actually, this part is not here, but for the VOH, because if you go with the resistive load, right?
Yeah,
So,
yeah.
yeah,
Uh,
in this one,
Here, yeah.
yeah. So when it is zero, then NMOS is basically cut off, right?
Yeah,
Then V0 will be VDD plus IDRL,
yeah.
right?
What is ID?
Yeah,
VDD
sorry,
minus IDRL.
V0 is equal to VDD minus IDRL, right?
Yeah.
So how much is a load? I mean, RL will be something because we are putting the
Yeah,
resistive load over here.
yeah.
So VO will never be equal to VDD, right? In that
No,
case,
if
when
ID is 0,
VI is equal to zero,
if
yeah.
ID is 0, then
Okay, because okay, and then how about then when okay, and then when Vi is equal to 1, then this one is NMOS is on, then VO should directly be connecting to the VSS, right? Then it should get a proper, it should be zero, completely zero, right?
no, that doesn't happen because ID will not reach the value of VDD by RL. It will be restricted by the current which is provided by the NMOS. Okay. So,
Okay,
if you
okay,
see
yeah,
this
got
plot here. Okay. Yeah. Okay. Yeah, that is what we are deriving it here. Okay, what is the lowest value? So this will be given by this equation out here. So it can become close to 0 if you keep an RL and Kn as high as possible. Then it can come close to 0. Okay. Okay. So now to calculate an VIL, so we differentiate this equation and substitute dV0 by dVi as -1. So we get the value of VIL. So this is the voltage which we consider for a noise. This can be straight away called as the noise margin low also, because it is from 0 to this value. So it is going to be noise margin low. In the figure, VOH should be on the y axis. Yeah, VOH is in the y axis. Should be on the y axis. VOH is on the y axis, right? This is VOH. VIL is in the
Is also there is a VOH at 5 volts.
here. Yeah, yeah. This is actually V in. So this is this value 5 volt is VOH. Okay, so that is corresponding to VOH. Okay, so that is what it is saying. Okay, that means it is VDD. That's all. VOH. Okay, so that is what it is shown there. Okay, now once we
Sir,
yeah,
a
yeah,
question here.
yeah. Tell me.
So at VIL, doesn't the NMOS, like it acts as it is in a linear region, right? Because the curve decreases constantly, and at VIH, it is similar to the saturation region because it is kind of constant there.
No, 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 no.
It,
It's the other way around. When at VIL, what is VDS, whether it is in saturation or not, will be dependent on VDS, right? If you have a large VDS, which if VDS is greater than V overdrive, right? VGS minus VT, then it is considered as saturation. So in this case, you will find here this entire VO output is very high out here. It is just started falling. So we have a high VDS. So that is why here it is in saturation. Whereas while we are coming here, VDS has fallen. So we now that condition of VDS greater than VGS minus VT will not satisfy. That is why we are considering this as in linear region. Okay, is it okay?
okay, yes.
Yeah, yeah. Okay. So now having found out an VIL, then we can use that. See, we have one equation here. In this, if we substitute V in, okay, by the value which we got here, if we substitute, we will get a V out, right? So that V out will be nothing but V out corresponding to VIL. Okay, so that is V out. There is no specific term for that. It is just V out corresponding to VIL. Okay, it will be slightly lesser than VOH. That's all. So these kind of things you can expect in your exam also. So once these values will be given here, so straightforward it will be putting these values and finding out the noise margins and things like that. Okay, so here a noise margin is VIL in this particular case. Okay, because this is 0 out here from here to here, right? The next is to compute an VIH by VIH here. Now, if you see here, we are assuming this transistor to be in the linear region in this particular case. So it is VDD minus Vout divided by RL, that is the current through RL, and here we are using the linear equation instead of a saturation equation. So V in minus VT. So now you can differentiate both the sides with respect to V in. So you get an equation like this, and then we substitute dV0 divided by is equal to minus 1, and also V in we are going to substitute as VIH here. So V in wherever we are going to put as VIH. Now here in this equation you will find an V out is available here. Okay, so we leave it as it is. So you get one equation which is having VIH. So you will find there are two variables here. One is VIH is a variable out here. V out is also variable as of now. But if you see the initial equation here also we can put this as VIH. So you get one more equation with V out as a variable. So you have equation 1, you have equation 2. So they are linear equations with two variables. So we need to solve those two equations and then get the value of VIH and once you find VH, you can find out V out also. So these are the two equations which you will get for VIH and V out corresponding to that VIH. Okay, so this is about the resistive load inverter out here, right? Now this is a curve which indicates how the VTC curve would change when we increase KNRL. Okay, so one thing was very clear that it will go close to V0, right? So this, if you see, this curve is going close to V0. Okay, another thing which you can observe out here is the slope. Right now, if you consider this as an amplifier, okay, amplifier is what V in. Right, for a small change in V in, there will be small change in current ID, and this voltage drop will be that current into this resistance, right? So delta ID and delta R. Now if I, that is the gain V, right? So if you see here, the slope or the gain is proportional to ID and RL, and ID in turn is proportional to Kn, right? Kn. So Kn RL is directly proportional to the gain. So if you keep increasing Kn RL, the gain will increase, and that is why you have a steeper curve out here. So so there are two advantages in increasing Kn RL. One, it will come as close to as 0, and also the curve will be steeper out here, right? So it will fall better. So it will give a better response. Okay, yeah, let me explain it one. See, what is this? This is actually delta V in, okay, by delta V out. Okay, that is the gain in the transition region. Okay, delta V in, delta V out by delta V in, that defines the slope, right? Now if you see, V out is given by VDD minus IDRL. Now if I differentiate it with respect to V in, so this will go, it will be delta ID by delta V in, right? So you will find a delta VD divided by delta V in, and this is a constant out here. So this is negative because with increase in voltage, output is falling. So that is why this negative comes out here. And ID, if you see, it is VGS minus. So if I put the delta ID divided by delta V in, still Kn is in the numerator, right here. That's known as the transconductance, right? So if you see in this from these equations, okay, the slope is dependent on Kn as well as RL. So if you increase K and RL, this slope will be steeper. Is it okay? Yeah. Okay. High RL means close to ideal characteristics. Yeah. Yeah. High RL. Yeah. Let me revisit that slide here. Where is it? Yeah. So if you increase RL, we'll get an close to 0, or we increase the size of the transistor, also will come close to 0. But like I said, there will be a trade-off. If you increase RL, the propagation delay will increase, and if you increase the size of the transistor, the static current will increase. Is it okay?
Sorry to disturb, sir. Can I ask one question?
Yeah, sure.
Yeah, sure.
Sir, actually, in the graph where we are using ID as K and VGS minus VTH whole square by 2, in the off condition of MOSFET, yes, sir. In the off condition of MOSFET, can we use this ID as this equation? Because when the MOSFET is off, so VGS is not playing any role and VT is also not playing any role.
Yeah.
So ID shouldn't be like VDD minus V naught upon RL. And one more thing, like when if we are decreasing the value of ID, as you said, like VDD is equals to V naught when ID is equals to 0, means tends to 0. So ID will be less when RL will be more. Means they are both proportional.
Can you just step by step? Can you just repeat the question? Sorry, I couldn't follow that.
Okay, so can you move to the next slide?
Here.
One more. I think can you one more at the last week when we conclude the our results. Yes, sir. Here. So here, if we see in there are two conditions. One is like when the MOSFET is on, and one is like MOSFET is off.
Yeah. Okay.
So when the MOSFET is off, shouldn't ID means ID shouldn't be this equation, because VGS is not playing any role when the MOSFET is off, and VG is also not playing any role. It is just simply a resistor and which is connected to a high voltage, and other side we are taking the output.
Yeah, correct. So it will be 5 volt out here. So here in that case, the equation stands good. Only thing is ID will be 0.
So if ID tends to 0, then RL should be a great value.
No, not necessarily. RL could be.
Thing is making that ID tends to 0. That's my question, because ID, yes sir.
RL is fixed. Say it could be 1K, 10K, whatever it is. Okay, if the MOSFET is switched off, right, and you have ID equal to 0, right, then you still have the entire voltage. Like we have a normal voltmeter. When we measure the voltmeter, okay, like we put it into a socket and measuring 230, right, there is no current flowing there, because it is as close and large resistance is connected in the voltmeter. So we are assuming we are not drawing any current from the source, so it is giving the terminal voltage 230. Same is the case here when we are trying to measure this voltage here and not trying to draw any current here. We get the entire VDD available here. Is it okay? Yeah. Okay. I understand your confusion is if there is a resistance, you will never get full voltage out here, right? Okay, but we are assuming a case where there is no current flowing in this resistance. So irrespective of the value of the resistance, you will get a full VDD here, right? And actually, if you put a voltmeter also, you will get the full voltage there. As long as the voltmeter itself is not consuming any current or consuming negligible current.
Because this RL is completely really less to that RL of the voltmeter.
Yeah, correct.
Okay.
I think I'm picking up a lot of noise from somebody. Can you just mute? Yeah, now it's okay, I guess. Okay. Yeah. Okay. So we discussed this. Now, after that, there was a modification in the logic and the family. Then came the NMOS logic. Okay. So here, if you see, there were two configurations which were used, right? So here it was the same NMOS used, and the NMOS was it was powered by, the gate was powered by VDD itself. Okay. So if you see, the drawback of this particular circuit is the output voltage was VOH in this case was VDD minus VT. That we know that NMOS is that we studied in our very first class. Still I have some noise. Okay, can you just somebody mute all of them, all of your mics. Okay. So if you see here, this is an NMOS out here. So if you see here, uh, uh, this is not an Darlington pair. Okay, this is just an diode which is I think somebody's mic is still on. I can hear some noise. Yeah. Yeah. Okay. I had to just mute all of you. In case there is an doubt, let me know. I'll switch it on again. Okay. So here you will find this NMOS. You are supplying VDD out here. So this is a kind of a diode connected NMOS, you can call this. This is a diode connected. So obviously diode VT will be dropped. So this is not an with perfect transmission or transmitter of one NMOS, we know. So the disadvantage was we had the total voltage not coming here, so noise margin got deteriorated, right, in this case. Okay, diode connected is like if you have the gate and the drain of an NMOS shorted like this, so it becomes a two terminal device. So it will act like a diode. Now if you see the characteristics here, so if you have an 0 here and up till VT, and if this VD, this is the terminal voltage, right? This can be considered as anode, this can be considered as an cathode. Up to VT, this will be off, because VGS is less than VT, and greater than VT, this will be on, and the voltage which will here will be 0.7 volt. That will be the dropout here. So it acts like an diode. So that is what it is known as an diode connected load. Okay, but again that VT drop will be here. So this is the relative simple fabrication process, but VOH was limited to VDD minus VT. Okay, where does the gain physically represent? Okay, there is a question. Okay, let me just explain this. I will go back to that. Right. So here, if you see here in this particular circuit, here there were two VDDs used. One was VDD here, and the gate voltage was here was VDD plus VTH. Okay, if you do that, then you will get a full VDD here, right? So because a VTH drop is scattered by giving a higher gate voltage here in this particular case. So you could do that. So once that is done, you will find VOH is equal to an VDD out here, right? So that is the but here the disadvantage was using two separate power supply. Okay, but both these circuits suffered from this high static power. High static power means whenever V in was high, there will be a constant current which will flow in these circuits unless a CMOS circuit. So both these circuits suffered from that. So if I take on that question here. Okay, now actually if you see this transistor, when I am operating in this region, okay, in this region, V in is equal to somewhere in between here. This acts like an amplifier, right? You can give a small signal here, you will get an amplified signal here. So you can use it as an analog amplifier. Okay, and that the gain, and that is the gain will be defined in that amplifier by the slope of this curve. Okay, delta V in by dn. So that is the significance of gain there. Okay, is it okay? Gain physically represents means it is the actual small signal gain in this region. Okay, you can use it as an amplifier there. Okay, now coming back here. Okay. Now after that there was an one modification. Is it an current amplification? No, it's an voltage amplification I am speaking here, because transistor the name MOSFET, they are all transistor. If you see BJT also, it is a transistor. Okay, the trans means in for a small input voltage change, there will be a change in the output current, right? So ID and VGS are related, and that change in VDS will be transformed into change in voltage by the circuit, okay, not by the transistor itself. In this case, because we have connected a resistance here, so a small change in VGS will result in small change in ID, okay, that is known as the transfer characteristics, and then from ID into R, that will result in change in voltage, okay. So that is how it happens. Okay. Okay. In the second figure, how VOH is equal to VDD. Okay. Here now you can give the output voltage out here. What it will be? Vout is equal to, right, VDD minus VTH, right. So in this case, if you the threshold voltage will be dropped across this, so you can have an increased VDD here, so that you get the desired V out here, right, threshold voltage. So you are using two different power supplies here. So that is the reason we are having these kind of circuits. Okay, so actually we have one logic voltage here and one increased voltage out here. So that is the two separate power supply voltage outs out here are required. Excuse me. Now then this family also, in fact, one I think the earlier 386 was fabricated using this technology, which is known as the depletion load nMOS inverter. Here you have a depletion load nMOS. Okay, so we considered earlier where the nMOS inverter, okay, and nMOSFET, where it was an P channel in between, right. So you had to give a positive gate voltage to make the channel. So an depletion MOSFET, we generally it's already an N channel is made here. So if you don't give any gate voltage also, then it is actually this type of connection will be called as a diode connected. Okay, this is not an actually diode connected. What we this is an load connected and load. It will be in fact this will always be in saturation region. If you see here, right? Why VGS VDS will be always greater than VGS minus VTH, right. Okay, so this is these transistors will always be considered as you will be in saturation. So we don't call this as a diode connected. This particular configuration we generally call it. Here it is depletion, but even if it is a normal MOSFET, when we connect it like this, we'll call it as a diode connected. Okay. So now if you have an depletion load nMOS out here, so if you see here, when we give an VGS is equal to okay, I think we can call this as an okay, we can call this as an diode connected nMOS. Okay, yeah. For PMOS, if you have like this connection, then it will become a diode connected PMOS. So this is an nMOS. Okay. So now we have a depletion MOSFET. So here VTH is negative. That means to cut off this transistor, you need to give a negative bias. Okay. So that is the reason. So when we connect it like this, and it continuously remains on out here, so you will have the full VDD coming here, right. So you don't you don't have that drop of VTH. Okay, we don't have the drop of VTH because VTH is negative in this case. Okay, because this is a depletion load. So this was used for making the earlier processors also. Right, here you have VOH is equal to VDD. We had a single power supply, but because a depletion nMOS was used, so it required some additional mask and additional processing step, but that was much better than these two topologies which had severe limitations. So here those limitations of having a VDD and single power supply both were met with this. So this was used for the first processor, CMOS nMOS based processor. This particular topology was used. Okay, so is it understood? Okay, so then we move forward. Right. Okay. In this depletion also, now you have we had a K into R, and now we have a KR, a factor known as KR, which is K driver divided by K load. Okay, K load is K of this transistor, right? So you will find K load. So obviously, if K is high, that means it is lower resistance. Okay, so it was KR in that case. So now R is inversely proportional to K, so that has come in the denominator out here. So these are the corresponding graphs for various ratios of KR is equal to K driver divided by K load. Okay, driver stands for the bottom one. Okay, sorry, here bottom one. And K load stands for the top one out here, right? Okay, so this was known as the depletion load out here, and then now we after that came the CMOS inverter. Okay, in the CMOS inverter, yeah, let's take a break out here. Okay. So just before the break, we were discussing what an CMOS inverter would be. In CMOS, we have an PMOS and as well as an nMOS out here, which are connected one above the other. Now, if you see when V in is equal to 0, this nMOS will be switched on and PMOS will be switched off. So whatever is the voltage available here on the node or at this node, that will be the charges which has been accumulated in the CL. CL is nothing but the gate capacitance of the next stage as well as the drain to gate capacitances of these two transistors. So whatever is the node voltage available here, that get discharged through the nMOS, and when V in is equal to 0, this nMOS gets switched on and PMOS gets switched on. Yeah, let me unmute. Yeah, I have unmuted all of you. So when this PMOS is off, then you will find this output node is getting charged to VDD. Okay, so this was the one, and this is has been has gotten great advantages over all the circuits which were discussed till now. The first and foremost is rail to rail output. So you had another for VO H it was 0 and VOL is 0 and VOH is full VDD. Okay, so that is that. It has got a full rail to rail voltage, and hence you have a high noise margin in this circuit. Ratio-less, right? So here you don't have to bother about what is the ratio, irrespective of the size of the NMOS and PMOS. You will find the output voltages VDD and ground for logic 1 and 0 respectively, right? The steady state, there is always an path between the output from the output to VDD or ground. And like if I see here, so it is it's not only for the inverter, for any static CMOS design. At any given point, there is no floating output. Okay, either this output will be connected to VDD or ground. Okay, so it is not something known as floating output where some stray charges are available at the output. So that doesn't happen in an CMOS design. Now always it will be either be positively connected to VDD or ground. Okay, so there will be a firm connection through transistors, obviously. Okay, and then the input resistance of a CMOS is extremely high. So steady state input current is 0. That means unlike an BJT, we are driving an CMOS, and when we are driving an CMOS, okay. driving a CMOS, if this is the next stage, the output will be connected to the gate of the transistors, and we know that there is no gate current is 0. So that is why it says input of a resistance of a CMOS inverter is extremely high. I'm again picking up some noise, right? Yeah. Can you please explain again for CL? Oh, okay. Let me cover these 2 points. I'll go back there. Okay. A single inverter can theoretically drive infinite number of gates. So unlike a BJT, where if you keep increasing the fan out, the current being supplied increases, and the VOH, the output voltage, even if it is 1, it can fall below the prescribed limits if you keep increasing the fan out. But that doesn't happen for an inverter here, because there is no gate current. So you can have infinite fan out. Only thing is, if you increase the fan out, the propagation delay increases here. Okay. And no direct path exists between supply and ground in steady state. Only during transient there is a direct supply between supply and ground. Otherwise, either the PMOS or the nMOS will be switched off at any given time, right? Okay. Now this CL, this is the load capacitance, right? So this is, what is this load capacitance? This is the gate capacitance of the next stage. Now also there will be some interconnect capacitance, and also between, this is the drain and the gate. So you have one capacitance out here, so that comes here, and you have this drain and this gate out here. So this CL is actually sum total of the drain to gate capacitance of these 2 transistors plus the interconnect capacitance, and also the gate capacitance of the next stage. Okay. So that is how an CMOS inverter. Okay. Now like we made an load line for an inverter, let's try and make it a load line for PMOS. Okay. Now in the load line, if you remember, we had plotted a V out and I out here, right? So in this case, if V out is 0 out here, then VDS is going to be maximum, right, for VSD in this case for a PMOS. And when V out is maximum, then VDD, it will be VDD here, it will be 0 VDS. So if you see this curve gets inverted like this, it is 0 here and it is maximum here, because V out is 0 here, maximum current, V out is VDD, minimum current. So this curve has got inverted here. Another thing which is important out here is, like for V in is equal to 0 here, VSG like will be maximum. So this topmost curve now corresponds to V in is equal to 0, and the bottommost curve out here will correspond to V in is equal to VDD. Okay. So these are the 2 changes with respect to nMOS. If you see the load line, because we are connected PMOS here as the load line. So let me try again unmuting all of you if there is no noise. Okay. Okay, let me I know there would be doubts, so let me repeat this out here, right? Now if you see here, V out, okay, V out, I am plotting V out here and the current here. Like if you see here, if I go back here to my first slide, this was V out, okay, V out, and this was the current which was flowing through the resistor. It came as a single line here, and nMOS curves was V out was same as VDS, and then a V in for because it's a 3-terminal device, for various V in we plotted here. Okay, and now we have an 3-terminal device in the load also out here, right? And so we are trying to plot the load line here out here, right? So for V in is equal to 0 out here, there will be maximum current flowing here, right? Here when V in is 0, there is no current here, so nMOS curve is like this. So now here it is become the VSD is maximum for V in is equal to 0, V out is equal to 0. So this is V out curve, right? And when V out is equal to VDD, then V SD will be minimum. So that is why this curve is like this. Instead of an nMOS curve going up like this, it will come from high to value of 0 out here. Another change which is happening out here is like V in. For V in is equal to 0, this is maximum. All right. So you will have a V in is equal to 0. This is the topmost curve, is the one which is there, and as V in increases, this curve keeps coming down. Is it clear to all of you now? Yeah, okay. So the load line is different out here. Now if I plot the load lines here, so the green ones are corresponding to the nMOS, and the orange lines are corresponding to the PMOS out here. Now if you see here, now if I consider a situation where V out is 0 out here, right, or V out is 0, if I consider here, let me consider a case where V in is equal to 0 first. So if V in is equal to 0, we know V out will be 2.5. So for V in is equal to 0, there are two curves. Okay, for nMOS, the one which is close to the x-axis. For PMOS, this is the curve for V in is equal to 0. So they will come and intersect at this point, which will be VDD. Similarly, if I take V in is equal to VDD, okay, then this is the then we for PMOS it is a 0 curve, right? So it will go close to the x-axis, and for V in this is the curve. So they will intersect at this point here. So if you join all these points together here, so you'll keep joining these points here. So you'll get the VTC curve out here. So initially at this point you will find an nMOS, PMOS is off, and at this point nMOS is off, and then in between you have both saturation. nMOS is in a resistive region or linear region, and PMOS saturation, nMOS saturation, PMOS in resistive region. So you will get this VTC curve out here, right? So if you keep intersecting these points out here, so the key takeaway from this graph is you will have a full VOH you will get as a 2.5 volt, like this is for an 2.4 VDD out here. So here also you will get a 2 point. So you will have perfect and a 1 and a perfect 0. Okay, so this is coming from taking the intersecting points like this here, right?
So I have a question.
Yeah.
I have a question.
Yeah.
Can you go to previous slide where the yeah? So let's say assume that for the first case, V in was 0.
Okay.
Okay, and in that case, V out was 1, right? In that case,
yeah.
When V in is 0, V out was 1.
Yeah.
And basically, that means in that case, PMOS was on, and there is basically CL is charging through the VDD, right?
Correct.
CL. Now, in this case, the potential difference between V out and VDD is same, right? Because then there is no current. There will be no current there, right?
Yeah. Once
Similarly,
it is charged, there will be no current. During charging, there will be current.
No, but it okay. So it will be so when it is 1 and the VDD is 0. When VDD is V out is 1,
yeah,
then basically PMOS is okay. You're saying in the initial value after a certain time V out will become 1.
Yeah.
So then in that case ID will be 0. So
yeah,
basically you are saying during the charging only this ID will be flowing. That is what you are saying, right?
Yeah, correct.
Then it is the otherwise is also the same. When V in is 1,
yeah,
then V out is 0, right?
Yeah, correct.
After a certain time.
Yeah.
But during this discharging through this one, then also there will be ID.
Yeah, correct. There will be an ID. Okay.
Right. So then. That part basically I get a little confused.
We will see that now in the next class. We will see the transient analysis, what is happening during switching. Okay. So how these currents will increase. Okay. Or after this, just immediately after
what
this
I'm
class,
saying is
I'll
what
show
I'm,
you a simulation.
So,
yeah.
So
No,
these are
what?
transient currents only, right? These are not
No,
static
no.
currents, because static current is always zero.
Yeah,
Yeah, actually,
static
static
current
current
means
will always
V
be
in
zero.
either will be 0 or 1 static current, right? So
Then in
in
that
that
case,
condition
ID
it will
will
be 0.
always be zero, right?
Yeah, correct. In that ID will always be 0, right? So
So
this
then
is in
why
between
this transient is showing
graph, right?
backwards?
This,
Yeah, yeah.
this graph is shown because while it's making a transition, we will come through these stages, and these currents will go like this high and it will come down, right?
Okay, so this is during the charging and discharging part only. But
Yeah,
every time, once it is 1 or 0, ID will
yeah,
always be 0,
yeah,
right?
yeah. I'll show you a simulation just after this, covering these slides.
Okay.
Okay, we will just clear these concepts again once again. Okay, so this is the VTC curve out here. Now there is something known as inverter threshold. Okay, inverter threshold is if you make a line where V in is equal to V out. Okay, like for at a 45 degrees angle to this axis, it will intersect a point that is known as VM. That is known as the switching threshold. Okay, of an transistor. Okay, so here in this particular case, it may not make a great sense here what is this voltage, but later on when we will see flip-flops and things like that, when two inverters are interconnected and all, so to make the change in state when they act as a latch, you will have to give at least an input voltage which is beyond VM and all, so that okay, we'll see that in details. Right now just understand it is just the center point of this particular curve. Okay, so VM. Now if you want to find out the value of VM, right, so you can equate this current, right, this is the nMOS current. Here lambda is taken and put here to take channel length modulation. So if you neglect that, then you can equate the PMOS and the nMOS, and we are assuming at that center point both this nMOS and PMOS will be in saturation region. So if you equate these equations, right, and then here VSG will be VDD minus V in, right. So VSG will be, here it is VDD and here it is V in. So you put that. So you put this equation out here. So we get a value of VMS VTN plus R into VDD minus VTP by 1 plus R, where R is nothing but Kp by Kn, right. So R is Kp by 1. So we get this equation. Now suppose we assume VTN and VTP to be equal. Okay, that is the case in most of the technologies. VTN and VTP will be equal, and we keep R equal to 1, then VM will be VDD by 2. If you see here, for a symmetric curve, ideally VM should be VDD by 2, right. So to obtain a symmetric curve, the requirement would be to keep VTH is equal, VTN and VTP equal, which is generally the case in most of the technologies. The next thing which we have to ensure is to keep R equal to 1, and R equal to 1 you keep by this equation, right. WP because the mobility of P is lower, right. So to compensate for the mobility factor, you will have to use the width is equal to greater for P. So for example, if you see here, the mobility of P is only 230 and the mobility of N is 580 around centimeter square per volt second. So if you see here, if you keep the W by L of P 2.5 times, and this 2.5 comes from this ratio, and that of N. Generally the L is also kept constant. So if you ensure that the width of the PMOS is 2 times the width of the nMOS, then you will find that you will get an symmetrical VTC curve. Is it okay? Okay. Why symmetrical is desired is there are several issues. One is to keep the noise margins equal. Otherwise, if it is an asymmetrical, you will find it is more prone to low noise, or if you keep this point here, it is more prone to high noise. Okay, so it is generally we keep it in the center, so that it is the maximum noise immunity on both the sides. Okay, so that is why it is desirable to keep it at center. Okay, so this is the thing which we need to take care as a designer, that we keep W is equal to VM. Okay, we'll see that. I'll just show you what is the relation of VM and noise margin. So if you see here, if you keep an KR is equal to 1, it is an symmetrical out here. Now if I keep an KR greater than 1, so this curve will shift towards the left out here, right? So because VM has now shifted, it has become lesser. Now it will shift lesser. Now if you see here, since it is shifted here, it has gotten a greater noise margin high, it has gotten a lesser noise margin low. Right now, similarly, if you keep the here, if you see here, the PMOS is kept, KR is greater, less than 1. That means KN is strong. If you keep the NMOS less than 1 means PMOS is stronger, so it will take that much more time. Since PMOS, if you normally you can understand that, right? If you keep PMOS strong, you have to give higher voltage to bring the output low here. So it is moving towards the right out here. So if you see here, now the noise margin high is getting adversely affected, whereas the noise margin low is better in this particular case. Okay, so that is what if you have to keep in the center, like rightly brought it, to keep the like Devdit said, noise margin low and noise margin high have to be kept equal here. So that is the reason we try and do the sizing accordingly, right? Now if you see here, for short channel devices, right, since the equation VD SAT becomes a limitation for the ID, right? VD SAT is nothing but an E SAT which we learnt there divided by L. So so the equations now slightly get modified, and now the only thing is, now you have to keep so if you see these equations, finally it boils down to VD SAT P by VD SAT N. Now if you see here, VD SAT in silicon for the holes and electrons is 6 and 8 into 10 to the power of 6. So you don't have to keep 1 here. For a long channel device, the P channel has to be 2.5 times the width of the N channel if L is kept constant here. Here it is not 2.5 because it is velocity saturated now. Now here it was because of the mobility factor. Now the mobility, the total mobility is not available, it is getting velocity saturated out here, and now the ratio is much lesser. So you can, if you see, that is the reason, if you see here for lower technology nodes, even 1 is to 1.1 or 1 is to 1 is also good enough, like they behave symmetrically. Okay, that is for the lower technology nodes. Okay, my observation is like for 45 nanometer technology, 1 is to 1 works fine, whereas for 180 nanometer technology, 1 is to 2 works fine. Okay, so that depends on actually the fab lab to fab lab, but this is the general thing which you can do. That you can do a simulation and find out what is the best ratio which is suited for the particular technology which you are using, right? So this is what again showing, if you have an beta going here, then it is moving towards the left, and here if you increase the beta, it's moving towards the right. Okay. Now if you see here, this is for the graph for the long channel devices, where it was a simulation was done for 250 nanometer and 2.5 volt VDD. So for 2.5 is the ideal one which we discussed. So you get close to 1.18 volt. But when the simulation was done for 2 volt, it gave 1.13. So there was not very much of a difference. So generally, as a rule for a long channel, we take 1:2. Okay, the ratio of PMOS. Okay, so it is always better to have a slightly lesser because the capacitance is going to increase the power and area, right? So instead of 2.5, we take 2, although there is small asymmetry is introduced, but that is okay. It's not a 0.05 volt only. So for long channel devices, as a working rule, we take the width of the PMOS to be 2 times that of an nMOS. Okay, so although theoretically 2.5 is the best one, but for practical considerations we take it as 2. Okay. Now, this is an graph on which we assume till VIH it is VDD. So for hand calculations and all, so this is how the graph is. Although it drops here, but this is for just for hand calculation. Sometimes we do take like this, right? Okay. Now the calculating VIL. Okay, so it was the same way we calculated the VIL for an resistor nMOS combination. We do the same thing. So here the nMOS will be in saturation, whereas the PMOS will be in linear region, right? When you go here, if I go back here, when it has started falling down here -1 slope, if I take nMOS VDS is very high. For PMOS, VSD will be very low, because on top you have VDD and below you have just VDD below VDD. So that will be in a linear region, right? So that is the reason here for the PMOS, for VIL calculation, we take PMOS to be in a linear region. So you equate these two. Okay, now you equate these two and then differentiate it, and after differentiating you take V out by V in as -1 and V in is equal to VL. You make this substitution, you will get one equation, and also from the initial equation where we have equated IL is equal to here. Here also you need to put because there are two variables, V out and VH. So you put these two there, you get two equations, and you solve that, you will get an equation for VIL. So it's not since L is constant. Yeah. See, L is also a design variable available with us. So if need be, we can change W, but generally we keep the length constant in digital circuits and accordingly adjust the value of W. Okay. So it doesn't.
Sir,
Yeah.
so we are considering here is IL is equal to ID, like nMOS current will be equal to PMOS, like
Yeah,
when is
yeah.
one is in saturation and one.
Yeah.
So basically both are conducting at this phase.
Yeah.
So should we not considering should we not be considering the charging current for the load capacitance?
No, we are finding out the DC characterization. We are not talking about the transient. Okay, so this VIL and the current which is being fed into the external load, that is not considered when we do the DC analysis. Okay.
Okay.
So we equate these two equations and we get the value of VIL, and a similar approach is done for VIH, and when we calculate VIH, we assume that PMOS will be in saturation and the nMOS will be in a linear region. So you equate those two, one equation, then you differentiate, and then put dV by V out by dV out as -1. You get the second equation, and then solving these two equations. So you can do some practice of computing VIL and VIH for your exams, right? So these are simple things only. So these things need to be known how to compute. Okay. Now if you see what are the when we are talking about a DC, let's just recall this which we did in the first class. We know that when we are going from higher towards higher technology node, VDD is decreasing and CL is also decreasing, but then to keep the propagation delay constant, we have to, since VDD is decreasing, we need to decrease VTH. And how do we decrease VTH? Now we have studied about the channel by increasing the channel. We have to increase. We have to decrease the channel doping, right? If you bring VTH close to VDD, then the leakage current increases. Like we saw in the channel region between N and P, there will be a reverse bias junction. So that if you are getting VDD close to VTH close to VDD, the leakage current increases. Okay, so that is the problem with the static leakage current. Like ideally there should not be any current, but there will be some current which will be flowing out here. right? So that is the now this is the current plot, you know, like somebody had a doubt. So if you see here, this is for 45 nanometer, which I did a simulation out here. If you see here, when Vin is equal to 0 out here, right, then the 15 picoampere is the current, because this NMOS, although it is supposed to be switched off completely, there will be some leakage current which is going here, which came to around 15 ampere. If I did it long time back, if I remember, I have used it as 1 micro and 2 micro width. Okay, so this is the 15 picoampere current. And then if you keep increasing this and you keep coming like this, if you will find the current is increasing in this region. When it is making a transition, then the current will be, both these transistors are on, and it will go up to 0.7 here, and then it will again fall out here, right? So this is when it is going high voltage, this is supposed to be switched off, but then you still have a leakage current. So the leakage currents of PMOS and NMOS need not be the same. Okay, from technology to technology they will be different. Generally the leakage currents in PMOS will be slightly lesser. Okay, now don't when we do this simulation, don't think that this will be the current which will flow when we are doing a switching, because this is just an DC switching. Okay, so when we do a DC analysis, these currents are correct what you get. Okay, but this current actually when we do a transient analysis, we will see that there are a lot of currents which will flow into the capacitor. Okay, like somebody just now mentioned, there will be currents which will going into the capacitor and all. So this current will not be the current which what you see in a normal DC analysis. Okay, so this current it is just an indication, but this is not the actual currents which you will see when we do a transient analysis. When we do an actual switching in time domain analysis, this peak current will be different what you see. Okay, there will be several other factors which we will see in the next class, but then this static current will be the same, because this is stabilized. So in what we do in DC analysis, these currents what we observe will be the same currents what you will see in the transient analysis also, when the input has got is not changing with respect to the time. Okay, so now to reduce the static loss, what we have to do is, for when we are working in this regime. Okay, if you are working in this regime, like for 400 width is this is the width is below 400 nanometer, right? In this region, if you use lower width, you will find, okay, VT is like if you are using higher width, VT is decreasing. Okay, so it is known as you can read this paper here. So you will have to use a higher width capacitance transistors to reduce the static current, but that is also generally not done, because if you use higher width transistors, then in that case your dynamic power increases, which we'll study in the next class. Okay, so this is just so in case you don't have any switching activity at all. Okay, you have some circuit which lies an ideal idle for most of the time, then probably you can use a transistor with a slightly higher width. Okay. Now there are other ways also to reduce the static loss. One is use multiple VDD. So these are the things which these days most of the modern processors they use these techniques, where it's known as dynamic voltage scaling, where suppose this is a critical path. Okay, this is a non-critical path. So actually the time taken for this signal to reach here will be say 5 nanosecond, whereas this is reaching at 10 nanosecond. So even if it is reaching at 5 nanosecond, I have to have a clock which will cater for this delay. So I can't have an clock which is as fast as 5 nanosecond, corresponding to time period of 5 nanosecond. So I should have a clock which will cater for this delay also. So in this particular path, since this is known, it is a non-critical path, I can use a low VDD here. right? So I can so this delay will increase, but still it is below 10 nanosecond. So this is known as a multi VDD. So this is known as dynamic scaling. So this is done in many places. And also the entire VDD also is reduced sometimes when you don't really require speed operations, like if it is just the computer is sleeping and doing some back-end operation where time is not a constraint, there also the VDD is reduced, the entire VDD is also reduced. Okay, so that is once more yeah, it is known as an power gating multi VDD. Like, see, there are two paths out here for signal to propagate. Here, if you see here, this path is taking 10 nanosecond here, whereas this path is taking 5 nanosecond. But since I have to cater for the longest delay to decide my clock, right? So say this signal is coming at 10 nanosecond. So I can have a clock maximum f is equal to 1 by 10 nanosecond. I cannot have f is equal to 1 by 5 nanosecond, because if I do that, then even before this signal comes, and I will be clocking this and I will get an erroneous signal. So this is known as the critical path. So my clock, the slowest path will decide my clock frequency. Okay. So that is the reason. So this is a non-critical path. This is the critical path. So in the non-critical paths, I can reduce VDD. So if I reduce VDD, then the power also will reduce, and the static power will reduce, and whereas the propagation delay will increase. Okay, but I will not reduce it to a value so that this becomes a critical path. This is still kept below this. Is it okay? Of non-critical can noise margin. No, VDD, yeah, it will increase the noise margin. Okay, so that is there, that will have, that effect will be there, right? So there is challenges of additional voltage requires to be created, or area overhead in power consumption. There will be a DC to DC converter required. Level shifters will be required, and multiple routing, but still it is done. It is worthwhile doing this. So most of the processors, in spite of all these constraints, it is done. Okay. There is another option which is available. Instead of decreasing the VDD in the non-critical path, we can use high VTH devices which will reduce the static power. Okay, so this is also done, right? Okay, this is also an equally good option, and it is also employed in many of the circuits. Okay, and a lot of research papers you will find where high threshold voltages and low voltage threshold voltages are used together. In certain paths, low voltages are used to speed up, and to reduce the static power you have a high VTs being used. Okay, so this is also an option which is available. No, the static loss is not dependent on the frequency. Okay, it's dependent on VDD and the threshold voltages. So for multi VTH design, these are the issues. You require additional masks, and but then you should have an additional library as a designer, where you can pull in low VTH, standard VTH, and high. So all those devices have to be modeled and given to the designer. But this is already implemented. These things are available. Okay. So with this we come to an end of today's theory.